I'd like to talk a little bit about the normal distribution that's presented in Chapter 6. Of course, you'll have to read and study the chapter, but a couple things I'd like to go over are how to do the computations for normal distributions and what the difference between this distribution and the discrete ones you studied in Chapter 5 were. Also, I would like to talk about the section in the chapter that talks about assessing normality and some of the assumptions we operate under when we do statistical tests. Anyway, to start with, probably the easiest thing to do is to show you how to do the computations in Microsoft Excel using PHStat. So that's pretty easy. It's pretty easy to do it by hand also, so I'll show you both ways. To start with, when we talk about a normal distribution, we talked about this earlier this semester, kind of in Chapter 3, where they talked about computing means and standard deviations and variances. And we talked about z-scores back then, and you learned how to compute a z-score. Formula does not change. So if you'll remember correctly, our mound or bell-shaped curve has some characteristics, mainly that it's defined by a mean and a standard deviation. Standard deviation determines, of course, the width of the curve. And you'll remember from reading Chapter 3 that approximately plus and minus 3 standard deviations on either side of the mean should account for, I think it's 99.7% of all the observations, which is a lot. Anyway, so actually the standard deviation, the z-score is just nothing more than a measure of how many standard deviations you are away from that center mean in your data. So to do this by hand, you use tables. And the example in the book, example 6.1, is a problem where he has given you data and says that its download speed, that the download speed averages 7 seconds with a standard deviation of 2 seconds. So the tables in your book are going to look the same as these tables, pretty much. Anyway, the ones in the book read from left over to the x value. So there are actually 2 pages of this standard normal probability table. They start at negative 3.4, some of them start at negative 3.9, and they go progressively smaller down the left side, and then the second page of it are the positive side of the distribution, so to the right of the mean. So they start at 0.0 and go all the way up to 3.49. In a way you read the tables is, whether it's on the left or the right, the z-score you should carry out to 2 decimal places. So if you have a z-score of 1.45, the first decimal, the 1.4, is read down the left side of the z-score table. So 1.4 would be right on this row. And then if it's 1.45, you would read across till you get to the column that has a 0.05 in it. That's the last decimal. And you can see your area would be this 0.9265. Excuse me. This is the area to the left, excuse me, of the 9. And then once you've got that figured out, you can read any value you want off the table. You can read intervals in between. Excuse me. You can read intervals in between the distribution between values, and you can do any computations you want with the tables. So that's the tables. That's pretty easy. The second thing, you want to know how to use PHStat in Excel, which is kind of painless. You don't have to do any calculations, and you don't have to look at any tables if you use PHStat. So I've opened up Excel with PHStat, and you'll see it's up here at the top. Click on PHStat, and just go under probability and probability distributions, the same place you went for your binomial and Poisson last week, which were your discrete distributions, and you look under normal distribution. And it wants a little bit of information. It wants to know what your mean is. Remember example 6.1, our mean was 7 seconds, and our standard deviation was 2 seconds. And it automatically defaults to probability that it's less than or equal to. That's what the table would give you, but we want the probability that's greater than 9 seconds. So I put the 9 in, and you'll see you can do a range in here, and pretty much anything you want. So say okay, and there's your answer, 0.1587. You remember the tables, the probability of it being and I didn't do the right one. So our z-score for that was 1.0, and for that example, and if you read across at 1.0, you get the area 0.8413 from the table. You go back to Excel and look at it. 1 minus that value, that 0.8413, is that area you see right here. So it actually does the computation for you without having to do anything else with it. So that part is pretty easy, the computations. But go back and practice them as you do your homework, and just make sure that they make sense, and do a number of different ones. The second thing I want to talk to you about is evaluating normality. We talk about normal distributions, and we discover that, let me go File, Open. When we look at distributions, no data is going to be perfectly normally distributed. It just does not happen in real life. So what you want is to do enough analysis of your data to determine that it's fairly normal. It's close to normal. There are a lot of tools that we use for statistical analysis that are based on the idea that we have fairly normally distributed data. Again, no data will be perfect. So some things we can look at. I'm going to go ahead and open up a file. This file is I have saved under your class materials, and you'll want to open this up too and have a look at it. And it's called Retirement Funds. I think we may have opened this up before, back in chapter 3 maybe. I can't remember, but anyway, retirement funds. And it's a big, huge file with a lot of information in it. So in the book, he talks about looking at the descriptive statistics for a data set that we're interested in, of variables. In our case, what we're interested in is the 1-year returns. So to do that, assess that, easiest thing again is to go to PHStat, look at descriptive statistics and descriptive summary, just like you did last week or a few weeks before, and put in the range of your data. So I'm going to move this so I can look around it, and just select all the way down. And then go back and single group variable, we don't have multiple groups. And our first cell did contain a label, so just say OK, and it should pop up with your descriptive summary. So here it is. You can see that, number one, if it's perfectly normally distributed, it'll be perfectly symmetrical. That means the mean and the median will be exactly equal to each other. You can see, looking at this, that your mean and median certainly are not the same number. And it gives you a lot of other information like standard deviation. The two things it gives you that are of special interest to us are skew and kurtosis. Skew is a measure of how spread out the tails of your distribution are. So if you get one that looks pretty normal but it's got a real long tail on one side, that's measured by skew. Left skew would have a negative number, which this one does. It's a negative 0.8961, and that just means it's got a long tail on the left. So I'm assuming for our return percentages, that means we've got some returns, a fair number of them that are really, really low and kind of skewed out there on the side, on the left. If you get a positive number with a skew, that of course means that it's got a right skew. It goes out on the right, so you'd have a lot of high values. And if you have a 0, that means that, of course, it's just perfectly symmetrical. Again, you'll never see perfectly symmetrical. So the skew is a minus 0.8961, suggests to us that our data has, something going on one tail end of it. Kurtosis, the other measure we're interested in, is measured at 1.1830 for this data. Kurtosis is a measure of the height of the center of our curve for our data. And if it's perfectly bell-shaped, perfect height, you'll have a 0 for kurtosis. If you have a measure that is a negative, that means that the distribution is just flattened out, kind of flat. And if you have a positive kurtosis, that means it's taller than you would expect with perfectly normal data. So you can see this data has a a positive kurtosis, which means it's kind of tall. It has a negative skew. That means it kind of goes out on the left end. The other thing you can look at, should look at with your data, is the normal probability plot, which you did, I think, for me back in chapter 3. So if I go to probability and probability distributions, normal probability plot, and again select the same data, the 1-year returns, it will automatically create a normal probability plot. I know you can do these using z-scores in Excel, but it doesn't make any sense to do more work than you have to do. So anyway, so here I'm going to say OK, and it should give me a normal probability plot. He has pictures of these in the book. Again, go review them. If you see a normal probability plot, if your data was perfectly normal, it would look very straight line up through there without a lot of curvature in it, because you can see that the curvature, it's got this hump in the middle. It goes up and then goes kind of back down. That is a sign that we have a left skewed data, which is exactly what we do have. We saw that with our skew. If it went down and was kind of concave, then that would mean we had a right skew in our data. So anyway, those are a couple of things to look at. Work on your data, work on chapter 6 assignment, and I'll see you next time.